calculate the available amperes in an existing manufacturing facility using NEC Article 220.35, one must first convert the total usage to kilowatt-hours. This is done by dividing the total usage by a conversion factor of 1000. In the example provided, the total usage is 958,080 kilowatt-hours. Dividing this by 1000 yields 958.8 kilowatt-hours. Secondly, determine the average load. This is calculated by dividing the kilowatt-hours by the number of hours in the period. To find the number of hours, multiply the number of months, which is 12, by the number of days in a month, which is 30, and then by the number of hours in a day, which is 24. This results in 8,640 hours. The average load is then calculated by dividing the kilowatt-hours, which is 958.8, by the number of hours, which is 8,640. This gives an average load of 0.111 kilowatts. Thirdly, convert the average load to amperes. This is done by dividing the average load by the voltage and then by the square root of 3. In this case, the average load is 0.111 kilowatts, the voltage is 480 volts, and the square root of 3 is approximately 1.732. So, the calculation is 0.111 kilowatts divided by 480 volts divided by the square root of 3, which gives approximately 0.120 amps. The calculation using NEC Article 220.35 results in an amperage of 0.120 amps. This may seem low and suggest that the premises may not be heavily loaded. However, it's essential to consider several factors. Firstly, the utility report only provides the total energy usage, not the actual electrical load. There may be significant non-electrical usage such as space heating or cooling, which would not contribute to the electrical load and would skew the amperage calculation derived from the utility data. Secondly, NEC 220.35 does not account for diversity. Diversity is the reduction in load that occurs when multiple circuits are unlikely to be fully loaded simultaneously. In many industrial facilities, there is a significant diversity factor, meaning that the actual peak load is lower than the sum of the individual circuit loads. Thirdly, if the facility plans to add additional machinery, the amperage calculated using NEC 220.35 may not be sufficient. This calculation is based on past usage and does not account for future increases in the load. While NEC 220.35 provides a rough estimate of available amperes, it's not a substitute for a proper electrical load analysis. It is highly recommended to consult with a qualified electrician to assess the actual load and factor in future expansion need. An electrician can conduct a thorough site survey, measure the actual current draw of existing equipment, and provide an accurate assessment of the electrical capacity and future expansion requirements. Furthermore, it is important to understand the limitations of using historical energy consumption data to determine available capacity. This method assumes that past usage patterns will continue in the future, which may not be the case, especially if new equipment is added or existing equipment is used more frequently. A more accurate approach involves measuring the actual current draw of all existing loads under normal operating conditions. This can be done using clamp-on ammeters or power quality analyzers. The measured current values can then be used to calculate the total load in the electrical system and determine the available capacity. It is also important to consider the power factor of the loads. Power factor is a measure of how effectively electrical power is being used. A low power factor can result in increased current draw and reduced system capacity. If the power factor is low, it may be necessary to install power factor correction equipment to improve the efficiency of the electrical system. In addition to measuring the existing loads, it is also important to consider the potential impact of any new equipment that will be added to the system. The electrical requirements of the new equipment should be carefully evaluated to ensure that the existing electrical system has sufficient capacity to handle the additional load. This includes considering the voltage, current, and power factor requirements of the new equipment. It is also important to consider any applicable codes and standards. The NEC provides specific requirements for electrical installations, including requirements for conductor sizing, overcurrent protection, and grounding. All electrical work should be performed by a qualified electrician and in accordance with the NEC. When performing an electrical load analysis, it is important to consider all of the factors mentioned above. This will help to ensure that the electrical system has sufficient capacity to handle the existing loads and any future expansion needs. A thorough electrical load analysis should include the following steps. 1. Gather information about the existing electrical system, including the size and type of service entrance, the capacity of the transformers, and the size and type of conductors. 2. Identify all of the existing loads, including lighting, HVAC equipment, and machinery. 3. Measure the current draw of each load under normal operating conditions. 4. Calculate the total load on the electrical system. 5. Determine the available capacity of the electrical system. 6. Evaluate the potential impact of any new equipment that will be added to the system. 7. Consider any applicable codes and standards. 8. Prepare a report summarizing the findings of the electrical load analysis and make recommendations for any necessary upgrades or modifications to the electrical system. Understanding the nameplate data of existing equipment is crucial. The nameplate provides essential information about the electrical characteristics of the equipment, including its voltage, current, power, and frequency requirements. This information is necessary to determine the load that the equipment will place on the electrical system. The voltage rating indicates the voltage at which the equipment is designed to operate. It is important to ensure that the voltage rating of the equipment matches the voltage of the electrical system. If the voltage is too high or too low, the equipment may not operate properly or may be damaged. The current rating indicates the maximum amount of current that the equipment is designed to draw. This information is necessary to size the conductors and overcurrent protection devices that will supply power to the equipment. The power rating indicates the amount of power that the equipment consumes. This information is necessary to calculate the total load on the electrical system. The frequency rating indicates the frequency at which the equipment is designed to operate. In the United States, the standard frequency is 60 Hz. It is important to ensure that the frequency rating of the equipment matches the frequency of the electrical system. In addition to the nameplate data, it is also important to consider the operating cycle of the equipment. The operating cycle is the amount of time that the equipment is in use. This information is necessary to calculate the average load on the electrical system. For example, if a piece of equipment is only used for a few hours per day, the average load will be lower than if it is used continuously. Understanding the different types of electrical loads is also important. There are two main types of electrical loads: resistive loads and reactive loads. Resistive loads are loads that consume electrical power and convert it into heat, such as incandescent light bulbs and electric heaters. Reactive loads are loads that store energy in a magnetic field or electric field, such as motors and transformers. Reactive loads can cause the current to lag behind the voltage, which can reduce the power factor of the electrical system. Considering future expansion is crucial. When planning an electrical system, it is important to consider the potential for future expansion. This includes adding new equipment, increasing the size of existing equipment, or changing the way that the facility is used. The electrical system should be designed to accommodate these future needs. This may involve oversizing conductors, installing additional transformers, or providing spare capacity in the electrical panels. It is also important to consider the long-term reliability of the electrical system. The electrical system should be designed to minimize the risk of downtime and to provide a safe and reliable source of power. This may involve using high-quality components, providing redundant systems, or implementing a preventive maintenance program. A short-circuit study is a type of electrical analysis that is used to determine the magnitude of the fault current that would flow in the event of a short circuit. This information is necessary to select the appropriate overcurrent protection devices, such as circuit breakers and fuses. The overcurrent protection devices must be able to interrupt the fault current before it can cause damage to the electrical system. A coordination study is a type of electrical analysis that is used to ensure that the overcurrent protection devices in an electrical system are properly coordinated. This means that the overcurrent protection devices should be designed to trip in a sequence that minimizes the extent of the outage in the event of a fault. For example, if a fault occurs on a branch circuit, the branch circuit breaker should trip before the feeder breaker tripped. This will prevent the entire feeder from being de-energized. Grounding is an important safety feature in an electrical system. Grounding provides a low impedance path for fault current to flow back to the source. This helps to ensure that the overcurrent protection devices will trip quickly in the event of a fault. Grounding also helps to protect people from electric shock. Surge protection is a type of electrical protection that is used to protect equipment from voltage surges. Voltage surges can be caused by lightning strikes, switching operations, or other events. Surge protection devices can help to absorb or divert the surge energy, protecting the equipment from damage. Harmonics are unwanted frequencies that can be present in an electrical system. Harmonics can be caused by nonlinear loads, such as electronic equipment and variable frequency drives. Harmonics can cause a variety of problems, including overheating of equipment, reduced power factor, and interference with communication systems. Power quality monitoring is the process of measuring and analyzing the quality of electrical power. Power quality monitoring can be used to identify problems such as voltage sags, voltage swells, harmonics, and transients. This information can be used to improve the reliability and efficiency of the electrical system. Load shedding is a technique that is used to reduce the load on an electrical system during periods of peak demand. Load shedding can be used to prevent overloads and to improve the stability of the electrical system. Power factor correction is a technique that is used to improve the power factor of an electrical system. Power factor correction can be achieved by installing capacitors or other devices that compensate for the reactive power consumed by inductive loads. Power factor correction can reduce the current draw of the electrical system and improve its efficiency. Energy efficiency is the process of reducing the amount of energy that is used to perform a given task. Energy efficiency can be achieved by using more efficient equipment, improving insulation, and implementing energy management strategies. An energy audit is a systematic assessment of the energy consumption of a facility. An energy audit can be used to identify opportunities to reduce energy consumption and save money. The NEC, or National Electrical Code, provides specific requirements for electrical installations. It includes requirements for conductor sizing, overcurrent protection, grounding, and other aspects of electrical safety. All electrical work should be performed by a qualified electrician and in accordance with the NEC. Local codes and regulations may also apply to electrical installations. It is important to check with the local authorities to determine the specific requirements that apply in your area. Permits may be required for certain types of electrical work. It is important to obtain any necessary permits before starting any electrical work. Inspections may be required after electrical work is completed. It is important to schedule an inspection to ensure that the work has been performed in accordance with the applicable codes and standards. Safety is paramount when working with electricity. Always follow safe work practices and wear appropriate personal protective equipment. If you are not qualified to perform electrical work, hire a qualified electrician. The calculation of available amperes using NEC 220.35 provides a starting point. However, it should not be the sole basis for decision-making regarding electrical capacity. A comprehensive electrical load analysis conducted by a qualified electrician is essential for accurate assessment and safe expansion. This analysis should include actual measurements, consideration of diversity factors, and adherence to all applicable codes and standards.